So let me continue the previous lecture. Previous lecture in which we have to show that the integral is independent of the representation of a step function. So we have seen that that lecture that integral of phi plus integral of phi is equal to, sorry, it was integral of phi plus phi is equal to integral of phi is equal to integral of phi plus integral of phi. So this implies integral of twice phi is equal to integral of phi. We had two representations for phi. So we had two integrals actually for phi, but on this side we have only one integral. I can write this as twice integral of phi is equal to integral of phi plus integral of phi. So let me take this integral as the integral of phi when phi has been expressed as a standard representation. Then phi is a standard representation, and this one is the integral with respect to the other representation. Okay, we choose two representations, and here I can choose any one of them. So let me choose on this side the standard representation is twice summation, or you can choose other representation as well. Summation I runs from 1 to n. It's what's it? It's ai mu star of ai, and on this side its first one it is a standard representation. Summation I runs from 1 to n ai mu star of ai, plus this one is the second representation. You can see the previous lecture. Summation g runs from 1 to n b j mu star of bj. Okay. So this implies on this side we have the same sums. Summation I runs from 1 to n ai mu star of ai plus summation I runs from 1 to n ai mu star of ai, it's equal to summation I runs from 1 to n ai mu star of ai plus summation j runs from 1 to m bj mu star of bj. So since it's a finite number, so that means summation I runs from 1 to n ai mu star of ai is same as summation j runs from 1 to m bj mu star of bj. So that means the integral is actually independent of the representation. If you take the standard representation, or if you take the other representation, both the integrals are actually same. So thus this integral is actually a well-defined function that I can say it's a well-defined function. So in the next theorem, we will see the certain monotone properties of a step function. Here, monotonicity of the integral. City of the integral. Monotonicity of the integral. For a step function is phi and psi, the following statement hold. For step function is phi and psi, the following hold. First one, if phi greater or equal to 0 almost everywhere, if phi greater or equal to 0 almost everywhere, then integral of phi is greater or equal to 0. then integral of phi is greater or equal to 0. And in particular, from this we can conclude, in particular, if phi greater or equal to psi almost everywhere, phi greater or equal to psi almost everywhere, then integral of phi is greater or equal to integral of psi. And the second part, if phi is equal to 0 almost everywhere, second one, if phi is equal to 0 almost everywhere, then integral of phi is exactly equal to 0. The value of the integral is 0. In particular, if phi equal to psi, then integral of phi is equal to integral of psi. In particular, if phi is equal to psi almost everywhere, then this integral of phi is equal to integral of psi. Integral of phi is equal to integral of psi. Okay. So let me put the first property of this integral. Suppose phi is greater or equal to 0 almost everywhere. So it may take negative values as well, because it's not greater or equal to 0 for each x. It's greater or equal to 0 almost everywhere. It's greater or equal to almost everywhere. And let's take this representation phi as a standard representation. Let phi equal to summation I runs from 1 to n ai characteristic function of ai. So these ai's a1, a2 up to an, these are the non-zero values assumed by phi. Since phi is greater or equal to 0 almost everywhere, so it may take negative values as well. But the set where it will take the negative value, the measure of that set must be equal to 0, because it's greater or equal to 0 almost everywhere. So the set where it will take negative value must be a null set, because it's greater or equal to 0. So therefore, if for some I, therefore if for any I with ai negative, for any I with ai negative, if you have any I in this set with ai negative, say suppose a1 is negative, and then measure of a1 must be equal to 0, because a1 is the value, the set of the points where it will take the value a1 is the set a1, and if it's negative, then measure of that set must be equal to 0, because it is greater or equal to 0 almost everywhere. So in general, let's take the value, say ai is negative, then this implies the measure of the set ai must be equal to 0, So if for any I with ai less than 0, then measure of the set must be equal to 0. Then measure of that set must be equal to 0. So therefore what will be the integral? Therefore the integral of phi by definition, it's equal to summation I runs from 1 to n ai mu star of ai. So it must be equal to greater or equal to 0, because for any negative ai, if there is some negative ai, then the corresponding the other factor of that, which is mu star of ai, is equal to 0. So it will be 0 into the negative number, that is equal to 0. So that means there remain only a positive numbers here, if any. So if all the numbers are negative, then measure of each set must be equal to 0. Then in that case, it's equal to 0. If there are some positive numbers, then its value is equal to that positive number actually. So in general, I can say it's greater or equal to 0. It's greater or equal to 0. Okay. So now suppose suppose phi is greater or equal to psi almost everywhere. This implies phi minus psi is greater or equal to 0 almost everywhere. Then you can apply this part because phi minus psi is a step function. This means integral of phi minus psi is greater or equal to 0, which implies integral of phi minus integral of psi, this is already done in the linearity property, is greater or equal to 0, and this implies integral of phi must be greater or equal to integral of psi. Integral of psi. So whenever phi is greater or equal to psi almost everywhere, then integral of phi must be greater or equal to integral of psi. Now let's prove the second part. Suppose phi is equal to 0 almost everywhere. This implies phi is greater or equal to 0 almost everywhere, and phi is also less or equal to 0 almost everywhere. So that by this integral of phi is greater or equal to 0, and from this integral of psi is less or equal to 0, because psi is less or equal to 0, sorry, it's phi here. Phi is less or equal to 0 almost everywhere. It's greater or equal to 0, here it's less or equal to 0. It means that integral of phi is equal to 0. So whenever phi is equal to 0 almost everywhere, then integral of phi is equal to 0. Now I will prove the second part of this one. Suppose phi is equal to psi almost everywhere. This implies phi minus psi is equal to 0 almost everywhere. Now I apply that part. It means that integral of this function, because it's a step function and it's equal to 0 almost everywhere. So that means integral of this function must be equal to 0. So now I can apply the linear property. It will be integral of phi minus integral of psi is equal to 0. So that means integral of phi is equal to integral of psi. Okay, so this proves the theorem completely. Now the next theorem is the order of continuity. It's the order of continuity of the integral. Order of continuity of the integral. It states that let phi n be a sequence of step function is let phi n let phi n let phi n let phi n let phi